All right, so now that we have our mechanical model in order to predict stresses, all what is left is just to obtain what are the material properties at the given site. And this is going to be done through a combination of field and laboratory data. In the laboratory, we're going to measure what are called static and dynamic properties. And in the field, particularly in wellbores, we're going to measure dynamic properties. We cannot measure static properties in the field. So what we're going to do is we're going to relate these two dynamic properties from the lab and the field in order to later obtain a static model of the field. So we'll have to combine laboratory and field measurements. But let's start with the dynamic. The dynamic properties, and these are the wave propagation properties, are going to be a function of the Young modulus and the Poisson ratio. So given, for example, the Young modulus and the Poisson ratio, these are going to define what are called the P wave velocity and the S wave velocity. The P wave velocity is given by this equation, which is the square root of something that we have seen. It's the constraint modulus divided the density bulk of the material. And the shear wave, Vs, is equal to the square root of the shear modulus divided the bulk density of the rock. If you remember what we call the constraint modulus, it was deformation just in one dimension. And this is actually what occurs when a wave, a P wave, passes through a solid. So let's imagine a three-dimensional solid from which we're just looking at a, you could call it like a bar within a three-dimensional solid. Then as a result of a P wave passing by, what we're going to have is just compression in one direction. So you can see from here that we have, for example, a P wave, let's add a coordinate system, which is traveling in direction, let's say, 1. And if I have just deformation in direction 1, then that's going to depend on the constraint modulus. And that's why the P wave is proportional to that modulus. So here the P wave is traveling in this direction. For the shear wave, it's the following case. If I have, again, the same prismatic bar within a three-dimensional medium, the shear wave is going to propagate by a distortion of this solid within the medium. So now the deformed configuration is going to look like this, where, for example, in this case, the shear wave is causing a distortion in the plane 1, 3, and is traveling in direction 1. All right. These two, as we see, there are these two waves, compressive or P wave, let's add the name, and the shear wave or S wave. They are a function of the shear modulus and the constraint modulus. And as long as we assume that this is an isotropic solid, we can solve as a function of the constraint modulus and the shear modulus, also the Young modulus and the Poisson ratio. Remember that for an isotropic solid, there are just two independent coefficients. So if you work through the equalities of between these two parameters, you will find out that what is called the dynamic Young modulus is equal to, well, what I'm writing right now, and it's a function of both the shear and the p wave velocity, and also proportional to the mass density of the rock. So in addition, for example, to acoustic logs that we may need in the field in the wellbore in order to measure this wave, we're going to also need to measure the density. And with density and acoustic logs, you're going to be able to calculate these two: dynamic Young modulus and Poisson ratio. All right, so I'm almost done with writing these equations. Let me check just the last one to see that I have the right value. Okay, so this is going to be equal to 2 times the difference of the squares of the velocities. All right. Okay, so these are what are called dynamic properties, and we can also measure these ones in the laboratory. However, as we were saying before, we are interested into the subsurface properties that are closer to the static deformation. And let's see what is the difference between this static and dynamic modulus, because eventually what we want is that static modulus. It turns out that the stiffness of a material is a function of the shear strain, and is a function too of the shear strain rate. So for example, if I were to plot the shear modulus of a given material, of a real material, as a function of the shear strain, I would find that for very small shear strains, the shear modulus is larger and starts to decrease as I increase the magnitude of the strain. For example, if I were somewhere around here in the order of 10 to the minus 6 or smaller, this would be the domain of the propagation of waves, very small strains. And if I were closer to field conditions, to, for example, what I would have close to a hydraulic fracture, then I'm going to be probably something closer to here with strains which are much, much larger and approach more the field conditions. So what I measure in a wellbore, for example, through acoustic logs is here, but what I want is in the field. I need to apply some sort of conversion, or I need to take into account this, what is called the degradation of the shear modulus. Okay, and let me add one more time over here. So I can have very large strains that even are in this range for the geological scale. And this stiffness of a rock is going to be also a function not only of a shear strain, but also of the shear strain rate. So I can do the same thing, plot the shear modulus. Now let me plot it as a function of 1 over the shear strain rate, where from here this means a derivative in time, so it's in a strain rate. And it turns out that the higher the strain rate, and therefore the smaller this ratio, the larger is going to be also the shear modulus. And the smaller the strain rate, also the smaller this shear modulus is going to be. And again, you know, I could also add, in this case, the range usually for elastic waves, the strain rate is very high. And here we also incorporate the effects of frequency. And as I move into engineering applications, that strain rate tends to increase. So if I measure properties around this region, both, and I want to get properties around this other region, then I need to take that into account. And usually what is done in these mechanical earth models is to simply apply an empirical conversion in the lack of some other more precise data that links the static Young modulus to the dynamic Young modulus to a conversion factor from static to dynamic, from dynamic to static, which is a function of the dynamic modulus. All right. Now let me tell you why I chose in the previous discussion the shear modulus, and we'll come back to the Young modulus. Usually the Young modulus, the same as the constraint modulus, they cause volumetric strains. And because they cause volumetric strains, the velocity of these waves, especially of the P wave, depends on the fluid within the rock. So if I want to discard all these effects caused by fluid saturation, it's easier just to look at the shear modulus, which it's the property mostly of the solid skeleton of the rock. That's why here we use the shear modulus. But back to practice, then what we usually do is to relate this static Young modulus to a dynamic Young modulus through this empirical equation. And this dynamic Young modulus, then I'm going to obtain that from if I'm in the laboratory, this is going to come from the ultrasonic elastic wave velocity, or the slowness, as you prefer, and the static Young modulus is going to be done through a triaxial test. Usually these two are done together at the same time. And in the field, then we obtain the dynamic Young modulus through an acoustic log. So if from the laboratory you have your static Young modulus and your ultrasonic wave velocity, then you can obtain this parameter FDS. And now, as soon as you do that, if you expand this to the field, then you can obtain, as a function of depth, for every position or every point recorded in the acoustic log, what is the static Young modulus in the field. The conversion from here to here, I have to tell you, is not trivial. And it involves many processes, which I also mentioned briefly over here, that depend on the viscoelastic properties of the rock and frequency effects. But to keep the discussion short in this lecture, let's just assume that they are similar. So this is everything then that you need. As long as you have laboratory tests and field measurements of the elastic properties, you can combine those and build finally a geological model that, combined with the tectonic strains and combined with other calibration data, is going to help you predict what is the horizontal stress at a given site. And we know that this is very useful, that, for example, for predicting the containment of a hydraulic fracture. Then if we want to predict what is horizontal stress and what is that containment, what we will have to do is to build a model that predicts what is the minimum total stress at a given site. And for example, for this made-up case, let's assume that it looks more or less like this, and then I get to a region where I have the horizontal stress, which is significantly lower. Here I'm looking just at an interval at a given depth, so this horizontal stress is not increasing with depth. And my objective would be, for example, if I were to perform hydraulic fracturing in this location, to see where that fracture will grow. And according to my model that I have on the right, for example, if I start a perforation here, very likely this fracture is going to start growing in this direction out of the plane, and is going to propagate down because it finds a lower stress at that location, and eventually growing out of the plane is going to look something like that. This information that we have on the right is what we have obtained from this mechanical Lerche model, and it's also what it's an input for hydraulic fracture simulators in order to predict the geometry and the propagation of hydraulic fractures. Okay, one more thing I forgot before I finish the lecture, and it is that, let me add it over here. Let me make some space, because this is quite important. I didn't mention what the value of this, of the coefficient FDS is, and let me do that. Okay, so over here, if you gather data from the laboratory, then this is usually going to look like this. You plot the static modulus in the y-axis, you plot the dynamic modulus in the x-axis. If this is a line in which these two are the same, your data would usually plot somewhere over here. And with this data, then you can obtain this empirical correlation, and tells you what is the static modulus as a function of the dynamic modulus, and the slope of this line is going to be this factor FDS, and this is going to be a factor which is smaller than 1. All right, so I believe I have covered everything for this section. There's one more thing I'd like to share, and so far we have talked about a modeling in one dimension, and we see that for this model in one dimension, just from the equations of a linear elasticity in this case, but just solving for a single point, we can arrive for an equation for the horizontal stress, even in the presence of the tectonic strain. And later we went into defining this sequence of layers in which all of them, they have a different Young modulus. In this condition, what I'm doing is I'm assuming that the layers extend infinitely in direction 1 and 2. But we know that in reality that's not the case. So you could go one step further and have a model in which we have the properties that also vary as a function of directions 1 and 2. And if you do that, what you are going to obtain is something similar to what I have in this image, in which now we have a prediction of horizontal stress, which is based on properties of the rock based on seismic properties, and they are not the same in horizontal direction, they vary. And as a result of that variation, we can see that we can find, in this case, sweet spots for hydraulic fracturing, or let me phrase it better, these are places where the minimum principal stress, in this case horizontal, it is the lowest in red. So all these regions have a lower horizontal stress than adjacent regions, and we can see that now with this model based on 3D seismic, we can extend this concept of fracture barrier that we developed in this case in one dimension, because we assume infinitely long horizontal layers, to a three-dimensional case. All what you have to do would be just to obtain properties with a similar workflow than the one we analyzed, and then put this together into a continuum mechanics simulator that will also see the principles about how to do that.